fellow group members did. You can do your own. You can take that copy, make a copy of it and change it, and turn it in independently. I'm okay with that. Okay. So now we're going to look at how do you decide which of the 4 types we've learned so far? How do you pick that one? Okay? And you're going to have to recognize which type of reaction it is from just the reactants. You're not going to be able to look at the products to figure out what it is because you're supposed to predict what the products are. I may have mentioned in the past that scientists are lazy. Okay? So I don't want to write out whole words. So for the purposes of this slide, E is going to stand for element, and C is going to stand for compound. Everybody okay with that complicated substitution? So, if they give me an equation that has 2 elements, this element plus that element, what kind of reaction is that going to be? Now, if I had something like, Na plus P, what kind of reaction does that have to be? How's the only way Na and P can change without making any new atoms? That would be to not be separate anymore, right? So if you got 2 elements, it's got to be combination. It's possible for 2 compounds to combine, but they would have to tell you it's combination. And then you're going to look for polyatomic ions. Because when you combine and make 3 capital letters, that means you got to have a polyatomic ion in there someplace. Right? But if it's just, I'd be able to expect you, if it's just 2 elements like Na and P, to predict that it's combination. Okay? If you had just 1 compound, the only way 1 compound can change is to not be by itself anymore, fall apart. So when somebody writes, how can H2O change? The only way it can change is to not be H2O anymore, which means the H's aren't hooked to the O's. Seem reasonable? Okay. So the next one is single replacement. What do you have to have if it's going to be a single replacement? You have to have a compound, something to replace it in, and you have to have something to replace, right? So you need one of each. Got to have a guy by himself and a couple on the dance floor. Or you have to have a gal by herself and a couple on the dance floor. Because metals replace metals, non-metals replace non-metals. Like on the quiz yesterday, the fluorine replaced the bromine, it didn't replace the strontium. Okay. And last we got was double replacement, and that was square dancing. And so to square dance, you got to have partners all around, right? So it's got to be all compound, 2 compounds. Okay. So let's try a few simple examples and see why we want to be able to name them. Okay. What kind of reaction is this? Is it combination, decomposition, single replacement, or double replacement? Well, is hydrogen an element or a compound? Element. Is oxygen an element or a compound? Element, so it's got to be a combination. The reason why you want to say that is combination is what's going to happen. They're going to combine. So I do what the name says. I combine them. Put H next to O. Then, this is a pattern you want to get used to. Do what the name says. Figure out the subscripts. H is 1 plus, O is 2 minus. That should be H2O. Then, balance. So it's do what the name says, figure out the little numbers, then balance. To balance this, I've got 1 O on this side, so I need to put a 2 in front of it. That gives me 2 H's. So we get 4 H's, so I got to put a 2 in front of that. Do what the name says, figure out the subscripts, then balance. So what type is this? Well, I got element and compound, so that is single replacement, so one thing replaces. So the one thing, zinc, replaces what? Hydrogen. Now here, replacing, we got to see if it's going to happen. And that's a activity series, so I'd have to go check. Zinc is pretty high on the activity series, hydrogen's low. This is going to happen. So the zinc is going to end up next to SO4, and the hydrogen is going to end up by itself. Get what the name says, one thing replace. Next, worry about subscripts. Does H need a subscript? Yeah, because H can't be by itself, so it gets a 2. ZnSO4, sulfate is 2 minus, zinc is always 2 plus. That's right formula for zinc sulfate. Then balance. One zinc, 2 H's, 2 H's, one SO4, one SO4. It's already balanced. It just happened to be that way, but I need to go through those 3 steps every time with every one I'm predicting. Do what the name says, figure out the subscripts. What kind is this? Well, I've got just one compound. How can one compound change? By not being one compound anymore, by being the separate elements that make it up. So this has got to be decomposition. It's got to fall apart. What would Hg2O fall apart into? Well, it would fall apart into Hg and O. Those are the elements. Now I decide, do they get little subscripts? Does Hg get a subscript? Not one of my 8, so it's okay. Does O get a subscript? Yeah, it's a 2. Now I balance 2 O's on the product side, so I got to put a 2 in front of mercury 1 oxide. That gives me 4 mercury, so I got to put a 4 there. Kind of reaction? No. Got a compound and an element. What kind of reaction is that? Still single replacement. Order is unimportant. The plus sign is just the word and. Red and green looks a lot like green and red. So this is single replacement. So the single is going to replace. The chlorine is going to replace bromine. Can chlorine replace bromine? Now look over here, chlorine's above bromine, so it can happen. So this is going to be K next to Cl and Br by itself. Single replace. Now figure out subscripts. Does Br need a subscript? K is 1 plus and Cl is 1 minus. That adds up to 0, so KCl is the right formula. So I did the subscripts, then balance. 2 Br, so I put a 2 in front of KBr, gives me 2 Ks. I put a 2 in front of KCl, which gives me 2 Cls, which I wanted anyway. And we got this process. You've done a bunch of these, right? But you see, but you need to get into that pattern of do the name, figure out subscripts, balance. Because what I get is, okay, I'm going to get this on the test, just so you know. I'm going to get KBr plus Cl2 makes KCl2 plus Br. I'm just going to copy the subscripts. Why is that wrong? Because it won't happen. K can't hang on to Cl. Br will never be by itself. It's a lie. Remember, these are sentences that describe what happens. This won't happen. That's why we can't write that. It's not just a bunch of letters we move around. It's describing what happens. Okay. All right, so last type. Type number 5. I really want you to get fired up about this type. It's called combustion. Okay. What is combustion? Well, it's fire, right? What does it take to have a fire? Well, you need fuel and oxygen. So you got some compound reacted with oxygen. And what we see when we see a fire is heat. We feel the heat and we see the light. You don't believe exists. Okay. Okay, so we're going to try to predict are compounds that have carbon and hydrogen and they might have oxygen in them. They have to have carbon and hydrogen. Because if you got a compound made up of carbon and hydrogen and sometimes oxygen, those compounds, they make very predictable products. So the combustion is different because you don't have to figure out the products. It always makes the same products. You just have to remember them. And they're worth remembering because they're the same products all the time. So, you're combining things with carbon and hydrogen and oxygen with oxygen. What you're going to make are things of carbon with oxygen, CO2, and hydrogen with oxygen, H2O. Say, excuse me, Mr. Green. Got a little problem. There's a fire. Where's the water? I have never seen water coming out of a fire. This is combustion, right? And I'm burning CH4. Right? So I'm doing what I said, made up of carbon and hydrogen. I combine it with oxygen. I'm going to make CO2 and water. I don't see any water. Looks like a lot. Well, if you got a gas stove at home and you've made macaroni and cheese, then maybe you have seen it. Okay? The problem is, it's making water vapor. It's just too hot. If I take this beaker with the water on the inside, I need the water on the inside to keep it cool. When I put it up over the flame, I see the water, see the vapor condense on top of it. It hits the cold glass, water vapor condenses. So that vapor on the outside is coming from the flame. So this is proof that the flame is making water. If you put a pan on the gas stove, like you're going to make macaroni and cheese, when you first turn on the gas stove, the outside of the pan gets wet. That water did not leak through the pan. It's from the flames underneath. So it makes water. Carbon dioxide is a little harder to prove, but water's pretty easy. Everybody believes it makes water? Okay. So Fire makes water and carbon dioxide. Now, sometimes the reaction isn't complete. It's called incomplete combustion. And if it's incomplete combustion, what happens is the oxygen is limited, so it can't make CO2. It only has enough oxygen to make CO. Carbon monoxide, the poisonous gas. Carbon dioxide isn't good for us, but it's not poisonous. Carbon monoxide is poisonous. Okay, so this time of year when it gets cold, what happens is the air inlets to people's filters gets blocked. Instead of their fuel making carbon dioxide, it makes carbon monoxide, and it backs up into their house. You know, a bird builds a nest in the smoke in the exhaust. All those gases are going to back up into your house. That could be carbon monoxide. And if the oxygen is really limited, it makes just carbon and water. And the carbon that they make carbon's not a gas, carbon's a solid. That's the soot you see. Soot is the carbon that's left over because you can have enough oxygen laying around. The black soot coming off the candle, that black stuff coming off the top, that's carbon that didn't get burned all the way. Because there wasn't enough oxygen. Somehow they were limiting the oxygen to it. Okay? O2 will always be the second reactant. You can't have a fire without oxygen. The most extreme fire suppression system I've ever heard of. My girlfriend's father worked in missile maintenance. I grew up in the military. And he was in charge of missile maintenance, where they worked on the nuclear cruise missiles. And the firefighting system in a building with nuclear cruise missiles is this. If somebody sends a fire, an alarm rings for 30 seconds. After 30 seconds, the doors lock, the room is sealed, and they pump out and they fill the room with helium, which pushes all the oxygen out, so the fire goes out. Now, if you're in the room, you have no air to breathe and you die. Okay. Why such a system? Well, because A, these are nuclear weapons. We don't want radiation going everywhere. B, these are nuclear weapons. They're tens of millions of dollars a piece. We can't afford to let them burn, but we can get more people to do missile maintenance. No, really, that's part of the calculation. We can get more people to do missile maintenance. That cost goes into it. But that was a great fire system. Get rid of the oxygen, you got no fire. That's how your fire extinguisher works. Our fire extinguisher, it's got a chemical that when heated absorbs oxygen. So when it absorbs the oxygen, the fire goes out. That's what happened there. Okay, so write the equation for the complete combustion of butane. What happens when I flick my bit? This is the complete combustion of butane right here. What am I making? Well, I know the fuel is C4H10. I know I can't have fire without oxygen, and oxygen's O2. What am I going to make? They tell me complete combustion. I know it's CO2 and water. It's not. I don't have to figure it out. This is not like the other ones where you're going to figure out the subscripts. It makes carbon dioxide and water. So, okay. Now all we have to do is balance it. Okay. 4 carbons, I put a 4 in front of carbon dioxide. 10 hydrogens, I put a 5 in front of water. That gives me 8 and 5, 13 oxygens on the product side. What number can I put on the reactant side and get 13 oxygens? I can't, because 13 is odd, and the other side is even. So I have to double the first one. right? So I don't have 4 carbons, I have 8, so I don't need 4 carbon dioxides, I need 8 carbon dioxides. I've got 20 hydrogens, so 5 waters is not enough, it needs to be 10 waters. And now I've got 16 and 10, 26 oxygens, so I can put a 13 in front of O2. I don't know if you noticed, but the ones that you balanced a lot of combustion reactions. You just didn't know they were combustion reactions, and they were the pains. It turns out about half the time you got to put that 2 in front. Okay? Combustion, about half the time you got to put the 2 in front, because you got that O2. So half the time it's going to be an odd number, and half the time it's going to be an even number. So half the time you're going to have to put a 2 in front. That make sense? Okay. What about the incomplete combustion of C4H10? I've got 2. There's 2 possibilities. Both of them start off with C4H10 plus O2. But there's 2 possibilities. I can either make carbon monoxide and water, or I can make carbon and water. Okay, I've done this enough to know, because we don't need to spend lots of time balancing equations. All of these get doubled. Okay. You don't need to see me balance lots of equations, right? So that means all of them have 8 carbon on the other side. All of them have 10 waters on the other side. Ever see that? The difference is 8 and 10 is 18 18 oxygens in the first one, so 18, I need a 9 here. And the other side is 10 oxygen, so there's a 5 there. Notice the difference between the equation. Why did I make pure carbon? Because I only used 5 oxygens. If I'm running short on oxygen, I can't do the top reaction because I don't have enough oxygen. So my first step down is to make carbon monoxide. And then when I run further down on oxygen, then I make the soot. So which one you make is going to depend on how well the oxygen can get to what you're trying to burn. Make sense? It's all about oxygen. So write the equation for the complete combustion of C6H12O6. Okay, here's where people make their first mistake. This has oxygen in it, but it's still the fuel. You still have to put plus O2. You have to add plus O2. It won't burn unless you put more oxygen in. It says complete combustion, so I just have to remember the products, not figure them out. Carbon dioxide and water. See, these reactions are worth memorizing because they work over and over again. The other ones you don't want to memorize, you want to figure out because every one's a little different. Okay, to balance it, 6 carbons, so I put a 6 in front of CO2. 12 hydrogens, so I put a 6 in front of water. That gives me 12 and 6 more, 18 oxygens on my product side. So you're tempted to put a 9 in front of O2, but don't do that. Because don't forget this 6 right here. So I need 18 on my reactant side, and 6 of them are already spoken for. So from the O2, I need 12 more. So this needs to be a 6. See how that makes it 18? So the mistakes people make is they don't put the plus O2 and try to balance it there, and it will never work. Or they forget to count the O. You do this. Hey, reaction look familiar? How if I turn it around? CO2 plus H2O makes C6H12O2 and water. Turned around, it was photosynthesis. This way, cellular respiration. Right? This is burning calories. Literally, that's why they call it burning calories. Because this is what happens to glucose. It combines with oxygen in your body. It makes carbon dioxide and water. Okay? And this answers an all-important question. When you go on a diet and lose weight, where does it go? Mass can't be created or destroyed, right? So if you lose weight, it's got to go someplace. Probably hadn't thought about it that way, but this explains where it goes. If you weigh yourself at night and then weigh yourself in the morning, I guarantee you'll be lighter the next morning. 100% guaranteed. Why? Because you lose weight by breathing. You're exhaling carbon dioxide. That's where the weight goes. Exhale. When you exercise, you breathe hard. Why? Because you got to get more oxygen in, you got to get more carbon dioxide out. For both reasons. You need the oxygen. Your muscles could do without oxygen for a while, but then we do some, the anaerobic exercise. But then you start building up lactic acid and it hurts a lot. Okay? That's because if you're doing anaerobic, you're not getting rid of the CO2, so that CO2 grabs onto some hydrogen and makes an acid in your muscles. Okay? So since the CO2 can't get out, it turns to lactic acid. That's bad. So when you lose weight, you're exhaling. So you can tell how much weight you're losing by how hard you're breathing when you're exercising. The water, say, oh, I lose water too, but the water you can't really count on because water A isn't going anywhere. It's still inside your body. It's a liquid, right? So you breathe your weight loss, which I thought was kind of bizarre. That's not what you think of it happening. That's not where you thought the weight was going before I asked that question, that you were exhaling. Okay? And C2H6O. It said incomplete combustion, two possibilities. But both of them have to say plus O2, even though they got O in there. Again, it's about, I don't have to figure out, I just have to memorize. I either get CO or I get C, and I always get water. It's not seawater. Because the carbon won't dissolve, it's not polar. That's why it's not seawater. Two carbons means I got to put a 2 in front of both of those. 6 hydrogens means I have to put a 3 in front of both waters. The bottom one has got 2 oxygen and then 3 more oxygen, 5 oxygen. And you say, oh, I have to double this. No, 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 you don't have to double this. Because I want 5 on the reactant side and one of them's already spoken for. So in front of O2, I only need 4 more. So that's a 2. Because that gives me 5 on my reactant side. Down at the bottom, 2 C's, 2 C's, 6 H's, 6 H's, 3 O's, 3 O's. We're done. Yeah. So this is a little bit different. It's easier, in fact. It's easier to write, it's harder to balance, because these are harder to balance than the double replacements, right? Because the double replacements, You bounce a few times, you end up done, right? Here, here the problem is going to be twos. About half the time you're going to get twos, or you're going to have to double. Okay? Just to let you know, that's where we're stopping. Okay? So on Monday, do a lab where you get to do double replacement reactions and talk about those net ionic equations. Tuesday. Wednesday we'll probably review. And then Thursday or Friday, test on types of reactions, what they're going to make. Not trying to surprise you. Okay? It looks like it's been going pretty good. The only mistakes I saw on yesterday's quiz was lots of people made the hydroxide mistake. The calcium in water doesn't make calcium oxide, it makes calcium hydroxide. That was the big mistake I saw most people make. And, all right, well, if I'm going to stop there, I gave you dead time. No, I don't give you dead time because you don't want dead time. Mr. Green assigned us like 3,000 homework questions. He's evil. He thinks it's a 4-day weekend. I should have 4 days worth of homework. No, didn't do that. Here's the first couple. And I'll put the next couple up in a few minutes. Okay. If we're coming to the end, I want you to review. So we're going back to writing and balancing equations, word equations. Go back to combination decompositions. Because we have done those in, because those were easy. We did those in a day. Single replacement took a little while longer. Double replacement took a little while longer. So I don't want you to forget that we started with the ones that were a little bit easier. Just so you can see, it says synthesis reactions there. Synthesis is another name for, you can tell, sodium plus oxygen. Right. Do what the name says. Figure out those numbers. We've got it. The name says. My wall too. The worst part's leaving for my hood. I'll freeze this side and do the next one's for the next one. What happened here? That one was supposed to stay.